Have you ever stopped to think about how your phone actually connects to a satellite? One that's hundreds of miles up in space. It's not magic, that's for sure. It's an absolutely incredible feat of engineering. So today, let's break down exactly how that first digital handshake happens.
Okay, to really get your head around the challenge here, you've got to understand the insane physics involved. See, connecting your phone to a satellite in low Earth orbit, well, it's nothing like finding a Wi-Fi hotspot at a coffee shop. It's way, way more like trying to have a perfect conversation with someone on a speeding bullet train while you're on another bullet train moving just as fast. Sounds impossible, right? And that really gets to the core of the problem, doesn't it? That satellite is just screaming across the sky at over 17,000 miles per hour. Your signal has to travel hundreds of miles up through space and land at the exact right spot at the exact right time just to be heard. I mean, seriously, how is that even possible? So this really breaks down the two massive hurdles we're up against. With a normal cell tower on the ground, everything's pretty stable, right? The signal delay is tiny, the frequency doesn't change much, but with a satellite, totally different ballgame. First, that huge distance creates a pretty significant delay. But on top of that, you've got its incredible speed causing this massive Doppler shift. Just think about how a siren's pitch changes as an ambulance speeds past you, that whooll effect. The exact same thing happens to the radio frequency. If your phone didn't account for both of those things, your signal would just be lost in space, literally. So how in the world do engineers solve this seemingly impossible physics problem? Well, believe it or not, the solution is probably already in your pocket. The secret weapon here is your phone's own built-in location services, like GPS. The technique they use is called pre-compensation, and it's pretty much what it sounds like. Before your phone even thinks about sending a signal, it compensates for both the travel time and that crazy frequency shift. It's basically predicting the future to make sure its message arrives perfectly on time and on target. The best way to think about this is like a pro quarterback. A great QB doesn't throw the football to where the receiver is right now. No way. They throw it to where the receiver is going to be. They see the target, they calculate the path, and they lead them with the pass. Your phone is doing the exact same thing, just with radio waves instead of a football. And this is the really crucial part. Your phone uses its GNSS chip, that's the system that includes GPS, to get its own super precise location and the exact time. It then mashes that data up with information about the satellite's orbit to do that quarterback calculation. It figures out precisely how early it needs to throw the signal and exactly how much to shift its frequency to make the perfect connection. All right, so the phone knows how to lead the target. It's got the math figured out. Now let's look at the very first step in the actual connection process. That initial hello from the phone up to the satellite. It all happens in two quick steps. First, your phone does all that math we talked about, calculating the exact timing advance and the frequency shift it needs. Then, and only then, does it send out its first signal. This isn't just any signal, though. It's a specially designed message called a RACH preamble, and it's already been perfectly adjusted to hit that moving satellite target. And hey, this isn't just some abstract theory. This is pulled directly from the official 5G engineering specs. The standards literally tell the user equipment, which, is just a fancy term for your phone, to apply these calculations to counteract the delay and Doppler shift. It's a fundamental rule baked right into the technology to make this whole thing work. Okay, so the phone has thrown a perfect spiral, right? The pass is in the air. Now, what happens on the other end when the satellite's base station catches it? How does it reply? The whole process is just brilliantly efficient. The satellite's base station detects that perfectly pre-compensated hello signal. Now, even with the phone's amazing calculations, there might be a tiny, tiny error left over, so the satellite measures any remaining offset. Then it shoots back a reply called a random access response, which basically says, "Got it, I hear you loud and clear. Now just fine-tune your timing by this teensy little amount." So this table really simplifies that whole initial exchange. The phone, the UE, sends the RACH preamble, which is basically, "Hello, over here." The satellite's base station sends back the random access response, which is like, "I hear you, now adjust just a little bit." It's this super fast two-step digital dance that gets that initial link established. So we've seen the incredible engineering of how this all works. It's pretty mind-blowing, but let's zoom out a little. Why is solving this incredibly complex problem so important in the first place? Well, this connection is what really matters. As soon as your phone gets that final fine-tuning command from the satellite, it applies the adjustment. And just like that, boom. In a fraction of a second, a stable 5G connection is locked in, and that opens up a whole world of possibilities. And the impact here is just enormous. This technology, which is officially known as 5G Non-Terrestrial Networks, or NTN, is what enables truly universal global coverage. I mean, think about it. Critical communications for disaster relief in the most remote areas, or connecting Internet of Things devices literally anywhere on the planet, from the middle of the ocean to the heart of a desert. So you see, solving the problem of how to hit a target moving at 17,000 miles per hour isn't just some cool technical exercise. It's what unlocks a future where no one and no thing ever has to be truly offline. Which kind of leaves us with a pretty fascinating question to think about. What are we going to create when every single inch of the planet is connected?